Hey everybody, welcome back to Math 20-1. We're going to be continuing on with the quadratics unit. And we're going to be looking at lesson 5, which is optimization problems. So let's get started. So to get going here, we're going to kind of backtrack and look at the three different forms of quadratic functions, the vertex, standard, and factored form. And so what I would like you to do is, going through past notes or memory, I want you to write down which characteristic can be determined through inspection and put an I there. And if it can be determined through inspection, let me know how you can do that. For the calculation bit, if it's something that can be calculated with a formula that's been given, make sure you include the formula. And X, maybe it can't be determined through inspection or calculation, but must be converted to another form by expanding and simplifying, or completing the square, or by factoring. Take a moment, pause the video, and come back and see how you did. So let's check it out. See how you did. I want you to go through what I've written down here. And notice that sometimes I put same as the vertex form. For instance, in the direction of opening, you can always determine that through inspection because we can all see the A value in each one of these terms. So we can do that right across the board. Some of them you may have put an X by. Notice that I didn't put on X anything because you can actually determine things through calculations if you know the formulas. If you don't remember the formulas, if they're not on your formula sheet, you can definitely transform one form into the other to find the missing information. So if you put X there, you're not wrong. So let's continue. So let's look at example 1. A spacesuit is thrown into the air from the deck of a spaceship sitting on a frozen ground of a distant planet. There is enough gravity that it eventually falls to the ground, and the height in meters of the spacesuit relative to the ground x seconds after being thrown is given by three quadratic functions below. So these three functions represent the path of the trajectory. So let's look at what I mean by that. It means that if this represents the deck of the spaceship, then we know that this thing is going to be thrown off the deck, go up, and then land on the ground below. And as you may notice, this represents a parabola. It's kind of like a partial parabola right here. And that these three functions in their different forms, we got standard form here is f of x, we have factored form here is g of x, and we have vertex form here, which is h of x, are all the same function written in different ways that map out this path right here. So their question is asking which function would allow you to most easily answer the questions. And as we could see from our chart before, there's always a way to find the information, but some are just more easy than others. And this one, we're looking for what's easy. Well, what is the maximum height of the spacesuit? Well, we are looking at this point right here. We're looking at the vertex. And if we want to find the vertex, we want to know the Q value for the maximum height. Well, the Q value in vertex form is 156.25, and notice it's positive. So we use the h of x, and we know the maximum height. And we're going to write it out because it's a word problem. Is 156.25. And because this has units associated with it, because remember it says the height in meters, we must include the meters as well, but you can leave it as an M. Now what about when does the suit hit the ground? Well, it hits the ground at this point over here, and that's an x-intercept. Now, we're going to go to the factored form, In other words, we're going to look at g of x to determine the intercepts, because we know that when we have g of x or any function which is like y equals a times x minus r, x minus s, that r and s represent the numerical value of the x-intercept. Well, we know in this one there are actually two. There are two x-intercepts. The first factor there tells us that x equals -5 is an x-intercept. And the second one here tells us x equals 20 is an x-intercept. But this has to be time. Remember, it says when does the spacesuit, not spaceship, hit the ground. And that has to be a positive number. So in other words, the time has to be the x value. So the time it hits the ground, or we can just rephrase it, the suit hits the ground at 20 seconds. Now let's move on to see what is the height of the deck of the spaceship. Well, I said that the deck of the spaceship was this point right here. This is where we're throwing that suit from. Now that suit on that deck is a certain height above the ground. Well, if we think of this as that XY plane, we know that this is the y-intercept. And the y-intercept is most easily determined when the function is in standard form or when we look at f of x, because we know that the y-intercept equals the c value. And in this case, the c value is 100. So the height of the deck is 100 meters. So let's move on to question 2. So question 2 says two quadratic functions in standard form are shown below, and it's asking how can you tell which of these functions has a maximum or a minimum? Well, we know that when a is greater than 0, and we can get this from our chart, we know that it's opening up, so therefore we have a minimum. Or when a is less than 0, it's opening down, so there's going to be a maximum value. So we know that, and we look at f of x, and for f of x, a equals 1, which is definitely greater than 0. So we know f of x is going to have a minimum value, and we know that g of x, that a equals -2, and that's less than 0. So we know that g of x is going to have a maximum. Now the next part here is asking us to write the function in vertex form. So we're going to be doing a little completing the square here. So looking down here a little bit, let's scroll down. We're going to start with f of x. Now f of x equals x squared minus 8x plus 3. The first step is we're going to bracket off the first two terms and take out a common factor of a. Well, the a in this case is 1, so we're done. The next step is to take half of the b value, divide by 2, and square it. Well, the b value here is 8, so we're going to say x squared minus 8x. Half of 8 is 4, or if you want, you can write it like this, and we're going to square it, and then we're going to subtract it. Actually, oops, get the eraser here going. Like that. And don't forget to hold on to the 3 at the end. The next thing is now we're going to bracket off the perfect square trinomial. We got one there now, and we're going to go ahead and rewrite that as x minus 8x. Now 8 divided by 2 is 4. 4 squared is 16 and minus 16. But remember, there is no a that we have to factor back in. So all we're going to do is combine these on the end and rewrite this as x minus 4 squared, and minus 16 plus 3 is negative 13. So the maximum value, the maximum y value in this case, is going to be the q value. So y max equals the q, which in this case equals negative 13. And my bad, it's y min. Now let's look at g of x. G of x equals negative 2x squared minus 24x minus 100. Now this one does have an a value that's not equal to 1. So what we're going to do, we're going to factor out the negative 2 from the first two terms. Just like that. Oops, I forgot the x. And that's as a starting point. I just want to double check that I wrote it down right. And I did. Perfect. So again, we're going to take half of the b value, square it. And we have to do add and subtract inside the middle. Well, 12 divided by 2 is 6, and 6 squared is 36. So we're going to add 36, and we're going to subtract 36. But remember, inside the brackets, because we got that negative 2 out front. I'm going to bracket off my perfect square trinomial, and then I'm going to distribute the 2 in after I make that look like this. So I'm going to go x plus 6 squared minus 36. Now I'm going to do that distribution. I'm going to take that negative 2 here and here, but I'm not going to forget I got this minus 100 sticking off at the end here. So what do I get? I get minus 2 times x plus 6 squared plus 72 minus 100. That leaves me with negative 2 x plus 6 squared minus 28. Now, same goes. This one we already determined had a maximum point, so the y max is going to equal negative 28. Now, all this talk about max and mins and where they occur brings us to this new idea of optimization problems. Every quadratic function we know has a vertex, and that means a max or a minimum point. If the function represents a quantity, then the vertex is the point where the quantity is optimized. And optimize comes from that word optimal, which kind of means like what's best. And this maximum point, well, we already know it's when the parabola opens down, and the maximum y value of the quadratic function is the vertex. This occurs when the a value is less than 0. We know all this, and we know the opposite is true is for the minimum. It's when it opens up, it has a minimum y value, and the quadratic function is at the vertex. This occurs when the a value is greater than 0. Now, we can determine these maximum and minimums from our chart. I just grabbed the chart and brought it here, either by inspection or algebraically, using PQ minus B over 2A and plugging that into the function to get f of minus b over 2a. And then over here for factored form, where we get the average, remember the average, r plus s over 2? And then we take that average and plug it in to get the y value, or the f of r plus s over 2. And we can also find these maximum minimum pieces graphically, and we can use it doing second trace and use 4 for max or 3 for min, and then following the procedure. Remember, if you're not sure, there is a calculator tutorial page on the website, so go ahead and take a look at that if you need some more help with your calculator features. Now, why is it important to know the max and min in problem solving? Well, sometimes we want to have a value that maximizes the profits, or we want to have a value that minimizes the cost. This is important. We don't want to spend too much money, or we want to make more money. So let's look at some problems where this might occur. Question 3. Identify the variable that is being optimized in each situation. And I want to draw your attention to the word identify. This just means to show what it is. It doesn't mean to solve. It doesn't mean to determine algebraically. It just means to identify. And it says where possible, identify the max or minimum value of the variable. So keep in mind, in some cases, due to the nature of the problem, we won't be able to solve it without, or determine it without just looking. We'll actually have to go in and solve it with a calculation. And we're not going to do that. We're just identifying. So the height of a curve on a mural can be modeled by an equation h equals minus 0.5 times d minus 4, where d is the horizontal distance from the left edge of the mural and h is the height. Above the bottom edge of the mural, all distances are measured in meters. So in this case here, we know that the maximum we want, because look what we got here. We got an a less than 0. That means this function is going to be opening down, which means there's going to be a maximum. And the maximum value here is h. So in other words, h is being maximized. And we can't identify what h is because this is in factored form. And even though we can write this out, one of the factors is d minus 0, because notice here we just have a d with nothing attached to it. Remember, without doing some kind of calculation, you can't determine the maximum. Now, the cost of producing widgets, and here, this is what I'm talking about, where we want to minimize cost. And we know this is a minimum because the cost per widget is given by C of n, which equals 0.2 times this. And notice this is in vertex form. Well, because the a value is greater than 0, it opens down and we have a minimum, and that's what we want. We want a minimum value. In this case, the cost, which is in C of n, is being minimized. And when you're producing things, you always want to minimize costs. Well, here we can actually identify the max or min because this is in vertex form. And we know that in vertex form, the y max or min, in this case min, is this q value, which is 136. Now let's look at the environmental clubs guys down here. They're having a fundraiser. And they sell 100 shirts a year at $40. And they're planning to increase the price. And so they've done a little marketing survey. And it indicated that if they increase the price by $2, that their sales will drop by 3 sales a year. So what should they charge to raise the most money? Well, let's identify what is being maximized or minimized. Well, notice the word most. This is a profit thing or a revenue thing. We want to maximize the revenue. So the revenue is being maximized. We want to know how much can we raise the price to improve the revenue coming in so we make more money in our fundraiser. In other words, so we want to raise the price to make the most money. And again, no equation is given. The information doesn't tell us what the maximum is. So we're just going to move on to D. Now in this question it says, of all the possible rectangles with a perimeter of 26, what does that mean? Well, we could have a rectangle like this, and I'll just give an example. Let's say that we have this side is 10, and this side is 10, and this side is 3, and this side is 3. This has a perimeter of 26, but the area of this thing is 30. Well, what if we adjust the lengths and widths so that the area is going to be more? Because we could do that. We could get an area that's bigger than 30 or even less. For instance, if we made this like, and of course not drawn to scale, if we made a perimeter of 26, such as, let's look what we got here. Let's say 9, and 9 is 18, and then we went 4 and 4. Well, look what we got here. Here the area is 4 times 9, which equals 36. So it's increased. So we want to know which possible rectangles will have the largest area where the perimeter adds to 26. Well, notice we're looking for the largest area. So this means that the area is being maximized. We're not going to solve it. We don't have enough information to find what that maximum is without doing a bit of work. But we definitely know it's going to be a maximized problem. Okay, let's move on. So question 4, the cost of tickets to the University of Alberta Golden Bears basketball game opening is $7. At this price, the 5,000 tickets will be sold, and a survey determines that for every dollar increase in ticket price, 200 fewer tickets will be sold. And it's asking us to complete this chart. So notice what they've done is here on the first column, the ticket price goes up by 1 every time. And on this side, notice what happens. With $1 increase, the sales go down by 200. And they're asking us to fill this in, so let's go ahead and decrease by 200 each step of the way going down. And then to get the revenue, and the revenue is the money they take in, notice all they do is multiply the ticket price by the number of tickets sold. So the revenue is ticket price times this, and let's fill it in. We get 41,400. Here we get 44,400, and this one we get 41,400 again. Now it's asking us in part B that the expression R equals 7 plus 1x times 5,000 minus 200x represents the revenue, R, generated by the sale of the tickets. How was this equation created, and what does x represent? Well, x represents the number of price increases. So for instance here, if x equals 1, 7 plus 1 times 1 is 8. So that is one price increase. So that would be this row right here. And then for the number of tickets sold, if x equals 1, 5,000 minus 200 is 4,800, and that represents the number of tickets sold. So this 7 plus 1 equals the price of the ticket, and 5,000 minus 200 times 1 equals the number of tickets that were sold. So 7 plus 1x, that represents ticket price. And 5,000 minus 200x, that represents number of tickets sold. And the revenue, or the money they take in, just equals the ticket price times number of tickets sold. Now the next question is, remember what limitations should be on the variables in this situation, and explain any assumptions that must be made in this situation. Well, let's think about the variables. Well, x. X is the number of price increases. Okay. What should x be? Think of the number systems. Can x be negative? Can x be decimals? Can x be what? What can it be? Well, if x is the number of price increases, we know that x must be greater than 0. If x equaled 0, there wouldn't be a change. So we know x must be greater than 0 in this case. So we have to remember context. And with context, you want to think about which number systems make sense. And you want to think about whether it can equal 0 or whether it can be negative. So look at all those things and you can make your decision case by case basis. But here, I think the real number system is going to work because we can increase ticket prices by a 0.25 or a 0.33. It's all good. We can do that with these. Now, the last part of the question asks us to sketch the graph of from your calculator and record the window setting. And I want you to give this a try. I want you to put this r equals 7 plus 1x and 5,000 minus 200x in, and I want you to play with the window settings. It's going to take a little bit to get there. So pause the video. When you get it all set up, come back and see how you did. So how did it go? Well, let's look and see what you did. Let's turn on the calculator here. So make sure when you do this that you're careful with your brackets. We want to make sure that 7 plus x and 5,000 minus 200x are both in brackets. If you leave off any of these sets of brackets, you're not going to get the right graph. Now, notice these numbers over here were kind of big, so we're going to need to make our window setting kind of big. So because I said that x had to be greater than 0, I put 0 as a minimum and 30 as maximum because I thought of x as the number of price increases. And I made the scale 5, and what I mean by that is those little ticks that you see on the axes. And same with the minimum value. Well, y also should be greater than 0, of course, because we're talking about money and we don't want to make negative money. But the maximum value, because our numbers were so big, I started with 60,000. Now, if you found a different number that worked and you could see the entire graph with a number that's a bit lower, that's okay. And I set my scale to 10,000s. So every tick on my y-axis will represent 10,000. So I hit graph. And there we go. See, you can actually probably bring this down a little bit lower if you wanted to, and it would still fit within. So notice every tick here represents 5. Every tick on the side here represents 10,000. So let's go ahead and draw that in. Okay, so this is what I have right here. X, we always put min, max, and scale, and we do the same for the Y. So let's move on to the next question, which is part E. Here it says determine the points below and explain the meaning of each within the context of the question. There's that word again. Well, the y-intercept, let me just scroll up a little bit here, that represents the revenue when there is no price increase. In other words, it's what we started at the beginning with. And so there, our y-intercept represents revenue when there is no price increase. I'm going to take it back. I'm going to say x greater than or equal to 0 in this case. Oh, and let's put in our y too. Y is also going to be greater or equal to 0 because we can make no money down at this end. Which brings us to the next piece. The vertex. Well, they didn't ask us that. Never mind. My bad. I misread it. So let's look then, let's keep going and determine the points below. Well, the y-intercept, we can go, that's the revenue when x equals 0. So that means I just plug 0 in for the x's and solve. We could use our calculator to do this, but you know what? Sometimes it's actually quicker to do it by algebra. So we go 7 times 5,000. And I'm running out of room. Let's squeeze it in here. 7 times 5,000 is 35,000. So if there were no price increase, the revenue would be 35,000. But the vertex, well, that's that little point up here. Well, that would be when the revenue is maximized. So it represents the maximum revenue with X price increases. So let's go ahead and figure that out. We're going to use our calculator for that one. And we're going to go second trace. And because it's a max, we're going to go for maximum. So let's go ahead and do that. So going back to the graph, we're going to go second trace for, we're going to go to the left. Patience is a virtue. Go to the right. Hit enter. Going to look between those arrows pointing at each other. And we get 8.99999. Like that. Equals y equals 51,200. Now, sometimes calculators, and mine is a virtual one, it does that 8.9999 thing. This can almost certainly be 9. I won't write it down just in case. We would actually have to put this in vertex form by completing the square to be sure. If I had to guess, though, it is. But let's just write 8.999. And the maximum revenue is 51,200. So how much should they charge per ticket? Well, they should charge $9 per ticket. Or sorry, not $9. They should have X equals 8.999 increases, which means that the cost per ticket, which is, let's say, price per ticket equals 7 plus 1 times the number of increases, and that's 99999. So that's 7 plus 8.99999, which equals 15.99999. But remember, this is money. We round money to 2 decimal places, and that means that this is going to be $16. So we're going to write that down. the cost to maximize the revenue is $16. Let's move on. So for number 5, two numbers have a sum of 16, and the sum of their squares is a minimum. Oh, look, this is a minimum problem. Da Vinci wrote the following to model this situation. Annotate his work. In other words, we're just going to talk about it. What decisions did he make? Well, first of all, he let A equals the first number and B equals the second number. So he knew that two numbers added together had the sum of 16. That word sum there equals 16. So he added them together, and then he decided to isolate his A. And he held on to that until he got over to the next part of the question. He said the sum of their squares is a minimum. Well, A squared plus B squared equals sum, which he called S. And then he said S equals A squared plus B squared. And he substituted this A here into that A right there to come up with this expression. The question now says algebraically convert Da Vinci's function into vertex form and determine the minimum sum and the two numbers. Well, let's start with what he has here. Well, first of all, let's expand this. So we got that thing squared right there. We're going to hold on to that b squared there. Now, when we expand this out, 16 times 16, that's 256, minus 16b minus 16b, a little foiling going on here. And notice what happens to the sign of negative b times negative b. We get that. Now we're going to gather the like terms, and I'm going to write them in descending order, meaning my square term is going to be first. So 2b squared minus 32b plus 256. I'm going to bracket off the first two terms because now we're at the completing the square part. And I'm going to factor out the 2. Now at this point right here, I'm going to take half of 16, which is 8, and square it, which is 64. And I'm going to add 64 and subtract 64. Remember, I'm going to close the brackets, but I'm not going to forget the 256. I know that those first three terms make the perfect square of b minus 8, but I still have to deal with the 64 because I have that 2 hanging out front. Now, so far, this is looking good because this should be a minimum and my a value is a minimum. So I know I should be on the right track. Now I'm going to distribute that 2 through. So I'm going to put it here, and it's going to be multiplied over here. So I get 2 times b minus 8 squared. Now 64 and 64, that's going to get me minus 128. And then I'm going to add the 256. And that's going to get me 2 times b minus 8 squared, plus 128. So it's half. So what is the vertex? Because the vertex is going to help us determine the minimum value. Because a is a lot greater than 0, we have a min. So the vertex is 8 and 128. So this means that this b value equals 8, which means what is that a value? Well, we have to go back to this formula up here. The a value equals 16 minus the b value, which is 16, minus 8, which is 8. Okay, so A and B are the same. And let's double check. S equals A squared plus B squared. So that's 8 squared plus 8 squared, which means that we have 64 plus 64, which is 128. Now it's asking us to verify this graphically in part C. And this is a great little thing to do when you have to do things algebraically, is check with your calculator. And let's put this in here. So we get 2 times x minus 8 squared. We can hit the square button right here. Plus 28. I've adjusted the window settings to these right here. And I am going to hit the graph. And sure enough, I have a minimum, which is what we were expecting. And then I'm going to go ahead and second trace. And this time I'm going to hit 3 for the minimum. And I'm going to go a little bit to the left. The cursor is right there. And I'm going to go a little bit to the right. It's right there. And I'm going to hit enter. And then I'm going to say, yeah, go for it and guess. Now again, here's this sometimes happens. It definitely happens on my virtual calculator. It also sometimes happens on my actual physical calculator. But really all that is saying when x equals 8, that y equals 128. So let's write that in. So there we go. I've set in a window setting that worked. Again, if you have something different, I had it quite high. We could have probably cut it off right here somewhere, and that would have been okay too. So as long as we can see this minimum piece, your window settings will be all good. Okay, let's move on. So for number 6, a farmer has 100 meters of fencing to make a small enclosure for some animals. They are considering building the 3 different enclosures shown below. So notice what we have here. We have one that only has one part, one that has been separated in 2 and 3. It's asking us to choose a variable to use for the length and width and label the dimensions on each of the diagrams. Well, let's go ahead and do that. I'm going to say, the length is the longer side, and that would be the width right there. With this one here, let's say this is the length again, but now the width is going to be the width of each little individual enclosure. And then for the next one here, same here, this is going to be a length, but this is going to be a width right here. Now it says to state any limitations on this. Well, we know that in this case, we have to say that L and W must be greater than 0. The reason in this case it must be greater and can't equal, and unlike profit where in revenue and money you can have 0 money and it makes sense, in length and width of shapes, if you reduce one of the dimensions down to nothing, you no longer have a dimension, you no longer have a shape. So for instance, if I decrease this down, well, if the W does not exist, then it's no longer a rectangle. It's just a straight line, L. So not only can we not have negatives, but we can't have 0 as well. The next thing asks us to write an expression for the fencing required for each enclosure. Well, this is a perimeter problem because we know that we have to make this 100 meters of fencing. We're going to cut it in places, bend it in places to make these different enclosures. So for the first enclosure in the blue, we know that 100 has to equal 2 lengths, because there's 2 of them on each side, and 2 widths. For the green one, we're going to say, same idea, there has to be 100, but now there are 3, oops, that's an equal sign, 3 lengths, but there's only 4 widths. And then for the red one, still 100, just got to make it stretch, has to be 4 lengths, but it has to have 6 widths. So we have all of these different versions for each different kind of enclosure. Now, the farmer wants the largest possible area, and it says write an expression for the area of each enclosure. Okay. Well, the area must equal length times width. Well, for the blue one, we can solve for L. So in other words, I am going to say my L equals 100 minus 2W over 2, which equals 50 minus W. For the green one, a little bit different. We still have A equals LW. Oh, and let's fill that in here. I didn't give myself very much room to work here, did I? I'm just going to go 50 minus W for the L times the W right here. What was I thinking? Now for this one right here, we have A equals LW as well. Let's solve for the L again. Well, in this case, actually, I'm going to be difficult. I'm going to solve for the W. This is going to equal 100 minus 3L over 4. Now that does reduce down a little bit to 25, but now we got this fraction-y thing here. But that's okay. We can work in fractions. We're not scared. We can do it. So this would be L times 25 minus 3 over 4L. And for the last one, and area equals length times width, let's solve for the W again. No, let's solve for the L again. So we say L equals 100 minus 6W, dividing everything by 4. And then that equals 25. And this gives us minus 3 over 2W. So this one is going to equal the L value, which is 25, minus 3 over 2W times the W. So notice you can switch between which one you're going to isolate and what your area is going to be in terms of. The first one, the area was in terms of W, the second L, and the third W, and that's okay. So let's solve this thing. Now it says to pick one of the three. Let's pick the middle one right there. Now we already have this lovely little equation. Now let's do it in green because it's the green one. A equals like that, 3 over 4 L. And let's go ahead and run that L through, so we get 25L minus 3 over 4 L squared. That's cool. Which means if I rewrite it in descending order, I get that. Well, this is in standard form, where it just so happens that the C value is 0. So we can actually algebraically determine it, the maximum value, because to find the vertex, remember we have that lovely little formula here where A is the coefficient of the L squared and B is the coefficient of the L. So we're going to go ahead and fill that in. We're going to go negative 25 over 2 times negative 3 over 4. And there we're going to get, well, let's put that in our calculator. Nah, let's not. let's go 25 over 2. Now, if we're dividing by a fraction, it's the same as multiplying by the reciprocal, like that. And that means we got a negative and negative, and that's positive, so that's why I don't have any here. This cancels, and that becomes 2, so I have 50 divided by 3. What does that give us? And that is approximately, oops, let me get the calculator out, 16.66 repeating. Now, we're not going to use this right now. We're holding on to this number. Okay, this is a rounded number. Now, this one is 25 times 2, which is 50 over 3. This is an exact value, and we're going to use this to determine the maximum value. Okay, we're going to use this to plug back into our original function to solve for W. Okay, so this is the L that gives us the max, because this is, L is kind of like the X or the vertex part right here. So that is the L that's given us the max. We're going to take that and plug it back in for our W. And we said that our W equals 25 minus 3 over 4 times, now we got this 50 over 3 right here. Oh, that kind of looks nicer because look, we got these 3's canceling out. So we get 25 minus 50 over 4. Well, that's 12.5. And 25 minus 12.5 is actually 12.5. So what is the dimensions? The dimensions of the green one are going to be, well, of one of the pens, this dimension right here, that's the one we're going for. The dimension of one of the 2 pens is going to be 12.5, and this is in, did they give us the meters or units? They gave us meters. So 12.5 meters times, now we'll use the rounded value here. We'll say let's say 16.7 meters. And there you go. Now you may notice in the notes that I did do this for the red one. So now you have 2 of them done. If you want to come back and do the blue one and check with your teacher to see if you've done it, that's great. Now let's look at F. F says the farmer has decided to use a barn as one side of the enclosure. How might the equation and dimensions change in this situation? Well, let's look at what would happen there. If I had a barn and I had one of the enclosures, we'll look at the first one here, that's length and width. Well, no, by using the barn, I've removed one of the lengths from each of the equations, regardless if it's the one with 1, 2, or 3 separate pens. So in other words, my new equation is going to be only 1L plus 2W. And well, what is this going to do? This means with the same fencing, or the same 100 meters of fencing, you're going to get more area. Let's keep going. Now, the last question here says 3 students were trying to solve a puzzle given the following clues. Clue 1. The unknown numbers are integers. The 2 numbers differ by 8, and the 2 numbers have a product that is a minimum, so a minimization problem. Use the variables for A and B for the 2 numbers. State any restrictions. Well, they already said that they must be integer values. So really, that's all the restrictions there must be. Now, the second part B here says the students wrote the following equations to represent clue 2. And it says for clue, the two numbers must differ by 8. But what does differ mean? Differ means that we're subtracting. So if we say A minus B, that must equal 8. So it's asking us which one of these guys did it right and which one of these guys did it wrong for isolating. Well, A is absolutely wrong. They added, and they said they equals 8. Now, student B tried to isolate for B. Now, if we did this with ours, we would actually get 8A minus 8 equals B. So student B is not doing it right either. What about student C? Well, student C said that A equals B plus 8, and if we did that with ours too, by adding B to both sides, we get A equals 8 plus B, and we can switch these around, so it means student C is right. Now, student C used a clue to write the product A equals A times B. It says use the correct equation from above to write a quadratic function that represents the product. Well, the product P equals A times B, and student C says A equals B plus 8. So let's make the substitution for A, that it's B plus 8, and we're going to keep the B going. So not foiling, distributing this, we get B squared plus 8B. Now here, A is greater than 0, which means we're definitely looking for a minimum, and that's what we wanted in the original question. Now, algebraically determine the smallest possible product and the two values of the two numbers. Well, we can do this a couple ways. In the notes, I've used the standard form to find that x equals negative b over 2a. But we can also do this by completing the square. We can say that we have b squared plus 8b plus half of 8 is 4. 4 squared is 16 minus 16. Notice here there was nothing sticking off on the end here, so we can actually leave it like this. And this gives us b plus 4 squared minus 16. This tells us that the smallest possible product is when y equals negative 16. In other words, that's that q value right here. So the q value is the minimum value because a equals 1. Well, what are the other numbers? Well, one number is when pointed to the wrong one, is the x value, which is b value, my bad, I'm mixing up my variables, negative 4. Okay, and I'm going to change this not to confuse everybody. This is the product. The minimum product is negative 16, and b equals negative 4. So we know one number. B is negative 4, minimum product negative 16. Let's find A. Well, we know that A equals B plus 8 from our student C up there. And so we put negative 4 plus 8, which equals 4. So we have the minimum product is negative 16, one integer, negative 4, other integer, positive 4. Okay, so I've put the value y1 equals x squared plus 8x. I've had to adjust my window setting because that minimum was low, so I had to put my y-min down to minus 20. So that when I hit graph, I can see the minimum point right here. So let's go ahead and go second trace, and we're going to find that minimum point. So we're going to scroll over, get to the left, get to the right, and find that point. And again, notice what my calculator is doing. It's negative 4. So that we know that b equals negative 4, a equals 4, and it works. Well, it's time for practice, and it's now the end of the lesson. If you have any problems with the practice work, please make sure you get in touch with your teacher. I hope you have a great rest of your day. Take care.